we are going to look at the rate at which the susceptibles change to the infectious compartment by looking at how those who get at those who get into the compartment and those minus those who get out of the compartment. So, and that leads us to a set of differential equations where we'll look at how the susceptibles change with respect to time and how the infectious change with respect to time and how the recovered change with respect to time. So we will have the S, the T, which will look at how those that come into the compartment of the susceptible minus those that come out of the compartment of the susceptible. Now, we said in our assumptions that there are no, the population is closed, there are no new people coming in, no birth, and therefore the in is 0. We don't have anyone coming into the susceptible compartment, but we have those that are coming out of the susceptible compartment, and that is beta out of n times SI. So this gives us beta, negative beta, SI, and this forms our first differential equation, which is equation 1. And then we get to the infectious compartment, and then we look at those that get into the infectious compartment and those that get out of the compartment with respect to time. That is in and then minus out. So the in that we have is these that are coming from the susceptible compartment going to the infectious compartment, and that is beta out of n SI minus those that are coming out of the infectious compartment and are going to the recovered compartment, which is gamma I. And then this forms our equation 2. So then we look at the recovered compartment so we'll have the rate of change from the recovered compartment, which is dr dt, which will also have in and then those that are getting out. The ones that are coming into the recovered compartment are gamma I minus 0, because remember we said no one dies from the disease. So this is 0, giving us gamma I. And this takes us to equation 3. So this SIR model is very, very important in studying the dynamics of an outbreak, because with this you are able to study what we call the R0 or R0. R0 or R0 is the rate at which one infected, it shows us how many secondary infections are going to come from one infected person. So in other words, how many people one infected person is going to infect. So the R0 is equal to, is calculated by having beta out of gamma. So, and then when we calculate this, so different models will always have a different formula for R0. And when we calculate this, we are able to tell how likely this outbreak is going to grow. For example, if we get an R0 that is greater than 1, we know that this outbreak is going to grow exponentially. So meaning, for example, if we get an R0 that is 3, it means one infected person is going to infect 3 people, and each of those 3 is going to infect 3 other people. So you see that outbreak is likely to grow exponentially, and so the methods or the interventions that the public health specialists need to come up with to cap that outbreak need to come in very fast. So it helps us also know how fast we need to come in with the intervention. But then if we get an R0 that is equal to 1, it means that this outbreak is going to grow at a constant rate. And so we are able to also know how much resources to allocate to this kind of outbreak. Then also, if we get an R0 that is less than 1, which is the most important, is that we know that this outbreak is going to keep reducing and it will eventually stop. And this is the most important thing that the public health interventions look at. The aim is to ensure that we have an R0 that is less than 1. How do they achieve this? They make sure that whatever interventions they are coming up with are going to reduce beta and then increase gamma, which is the rate of recovery, and while reducing the rate of infection. So the public health specialists are also able to study the outbreak curve to know at what point in time this outbreak is likely to be at its peak and how long it's going to stay here at this peak before it can actually drop. So this is a very important model that we need in order to study the dynamics of a disease or of an outbreak. Thank you.